you guys how I measure a slab. What I'm gonna do is I'm gonna use an instrument called a zip level, or the trade name is a zip level. The generic name would be a CompuLevel. And what we do, or what this is the CompuLevel is a meter that's attached to a line that contains a liquid and a gas. And so this meter that I'm gonna show you here, this is gonna tell us how high or low the slab is. Okay, this is gonna register our measurement. And so what I do is I unfurl the line here, and I'm gonna pick a point. Remember, I've drawn my diagram. I've drawn a diagram of the house to scale on the outside. I've marked all my exterior stress signs, and now I'm ready to take the elevation survey. And so what I'm gonna do is I'm gonna take this meter and I'm gonna pick a reference point, okay? That means a point where I'm gonna set the meter to 0, okay? So that every measurement that I take from there is going to be relative to that reference spot. Now the reference spot is an arbitrary spot. It could be anywhere. It could be on the street, it could be on the roof, but that's not very easy for me to do. So I'm gonna do it towards the middle of the house because it's easy and it's easier to explain to a homeowner what's going on with their elevations. So what I'm gonna do at this point is I'm just gonna simply set this to 0. Okay, you can see if I lift it up, you see how it'll register. But I want it to be at 0. I want to figure out how high or low the floors are and the rest of the house relative to this point right here in roughly the middle of the house, okay? Again, it doesn't have to be exact. So I'm gonna go straight back here to the back of the house. This is just straight back to the back of the house from my reference spot. Okay, so I can see that from my reference spot, this point reads 2/10 of an inch lower than the reference spot, okay? And so I'm gonna take it to the corner over here. Okay, so here we can see we're about 1.1 inches down. I don't know if you guys remember or not, but there's a crack right down the wall just on the other side here. So that's probably why that crack is right there, because this is settling. So I've gotten a complete set of elevations now. I've taken elevations inside the house. I take them in the garage as well. The garage process of taking elevations is a little bit different because we do it from the ceiling. But now what I'm gonna do is I'm gonna go and I'm gonna look at my diagram where I've plotted all of my measurements. I've got all of my stress signs written down, and I'm gonna explain how we determine if a house like this has a problem or not. Okay, so now that we've evaluated our house and we've walked around, we've drawn it up, we've marked all the stress signs on our house, we've taken a floor elevation survey. So what I do then is I take my diagram here, and my diagram is drawn to scale, and I've got all my stress signs marked where you can see these markings. This spot right here on the side is 1/10 of an inch lower than the reference spot. And so what I do is I take all of this information and I look for 3 different things. I look for 3 different criteria to establish if there's a problem or not. First, I look to see if there's a deviation in the elevation pattern. Okay, a clear, I guess a really easy example of that would be if I had a slab that was rectangular in shape, and imagine that 3/4 of that rectangular slab measures within 3/10 of an inch. And then the other quarter of the slab measures 2 inches down. That would be an example of a clear deviation. So that's criteria number 1. So in terms of our house that we're looking at here, I can see that if I cover, and I'm gonna have a little bit of a hard time doing this, but if I cover these numbers up, and I cover these numbers up right here, and I look at these remaining elevations that you may be able to see well or not, but they all measure mostly within about 1/2 inch, okay? That's really good. That's what I like to see on a house that doesn't have a problem typically. When I move my hands, then I can see where I'm down 1 inch, 1 inch, 1.2 inches, 0.9. I'm at 1 inch all the way up here. And then in the garage, I'm 2.9 inches and 1.6. So that is what I mean when I talk about a clear deviation in the elevation pattern, okay? So that's criteria number 1. Well, a deviation can be constructed in. And so the second criteria is more important than the actual deviation. And that second criteria is stress. I've got to have stress to accompany the drop to tell me that the house moved into that position versus being constructed into that position. So then I can simply look at my diagram and see that, okay, well, I've marked a crack here. I've marked some separation at the freeze board here and at the garage door frame here, and some more cracks and separation up this side, some in the back. So I do have stress signs, cracks, separations, to indicate that this deviation is due to movement. Okay, so that's number 2. So we've established we've got deviation and we've got stress to accompany it. The third thing that I look at when I look at this is I look at the elevations, the numbers, the measurements, relative to the American Society of Civil Engineers guideline. Okay, now this is the guideline that builders use when they construct a slab, but they don't always get it right. And so I can have, again, a deviation that's beyond that guideline that I don't need to do anything with because I don't have any stress, okay? But that guideline, to boil it down, is 11/16 of an inch, which is about 0.68 or about 7/10 of an inch over 20 feet, okay? So then I'm gonna take these numbers and I'm gonna compare it to that guideline to see where I fare relative to that measurement or that number. And I'm gonna take an easy example here. I'm gonna say from this point right here, which measures 0, to this point right here in the corner, this will be our front porch area. So this is the corner of the front porch inside. We measure -0.8. So this distance from this 0 to -0.8 or 0.8 of an inch low is about 10 feet. Okay, our guideline is 7/10 over 20. So if I double this to make it 20, that means I'm 1.6 inches low over 20 feet. And so you can see that that's more than double the guideline of 7/10 over 20 feet. So that's how that works. There are exceptions to that. You know, I talk to a lot of numbers people, CPAs or engineers, and they kind of glaze over when I talk about that number. But that number is not the end all be all. So sometimes I have to kind of talk them off of that number and tell them, well, hold on, we also have to look at the stress, we got to look at the deviation, the overall picture. Let's not just focus on the numbers, because I may have numbers that are beyond that guideline where nothing needs to be done, and I may have numbers within that guideline where we do have to do something. If a house was constructed like this, for example, and part of it fell, I'm gonna have numbers that are beyond the guideline that we don't do anything, and numbers within the guideline that we do. So I've got to be careful like that, and that's why you need a seasoned professional to be able to make heads or tails of the data that they get. So I meet all 3 criteria. I've got deviation, stress to accompany it, numbers beyond that guideline. So I know that I need to repair this slab. I know that I have a problem. And so what we do to repair it, wherever you see a dot on my diagram, represents where we need to place piers underneath the slab. Okay. Now there are 3, so you'll see that they're dots all the way around. They're all the way around the back here. Okay. I'm kind of going stress sign to stress sign. These are just zeros, so that means that these measurements inside are relative or are even with my reference spot. But these dots that you see here and the ones that are circled just mean that we have to go through some concrete on the driveway and on the front porch. Okay. But anyway, each dot is equidistant, or as close to equidistant as I can get it. On a house like this, a 1-story, traditional home, it's gonna be about every 7 feet. On lighter structures, we might be able to go about every 8 feet. On a 2-story house, typical construction, we're gonna go about every 6 feet, okay? So the way that we place these piers wherever you see a dot is that we hand dig a 2x2 foot square hole about 5 foot deep enough to get a crew member underneath your foundation. And then what we do is we take a hydraulic ram, which is a machine that fits on a cart, a cart that you can pull behind you, just to give you an idea of the size, like you would pull at a nursery to move flowers or bushes or something like that. Right. And what they do is they take that ram and they put it underneath the slab, using the weight of the slab, engaging the ram, and they push 1 foot, I'm gonna put this down here, 1 foot by 6 inch in diameter cylinders of concrete called pilings into the ground. Each piling is real dense, thick, and heavy, and it's got a hole that runs to the middle of it. That's really important. That hole is important because that allows us to use an alignment system with our pier. That means that when we push these pilings into the ground, we need something to keep them going straight down into the ground, and so we put steel rebar in them continuously to keep them going one after the other so that they'll stay straight. Something that we see often in the industry is that pilings will be placed in an unaligned fashion, and that just means using solid cylinders or pilings that they'll drive into the ground, and when you do that unaligned, there's a risk of misdirection as you go down. Now the goal with these pilings is that you want to drive them to what's called the refusal point. Refusal, simply put, is the point at which the pilings will no longer go down and the house starts to go up. There are two types of refusal. There's true refusal, which is the one that you want, and there's false refusal, which is the one that you don't want. If they're misdirecting underneath, they can, in a sense, create their own load-bearing strata and stop prematurely. True refusal is a function of the weight of the house, the depth of bedrock or a load-bearing strata. We know bedrock can be really deep in Houston. So the other function would be the skin friction of the pilings with the soil around them. So if they're misdirecting and creating their own load-bearing strata, stops prematurely, boom, false refusal point, okay? That's one problem with an unaligned system. The other problem is that once they're built up to the house, because remember we started 5 feet down, it's built up to the house once the refusal point's hit and then capped off. Well, if that house is set on top of that pier and the ground or clay ground swells and shrinks as it gets wet and dry, that pier can simply fall apart, which is something that we tend to see after big rain events and things like that, but something that can be easily prevented by simply using an alignment system through the pier. So once we've hit refusal, we've built it up to the house and we put a cap on top. The cap allows us to lift off of that pier. It just gives us a base so that we can put a hand jack then on top of the pier. And then what the crew chiefs do is they'll line their crew guys up in these holes and assign, manning a hand jack, and they'll assign each crew member manning a hand jack a number or a number of times to lift on the jack. And then they count 1, 2, 3, and those guys pump those jacks to whatever count they're assigned, and then they stop and they lift the house in the process. Once they're done, what they can do, and I can show you an example here. This is a straight line of rebar that runs through the column of these pilings that construct our pier. We build it up to the house, put that cap on top. The cap's actually rectangular. That gives us a platform to lift off. They've lift off that platform, and then they can put another piling on top of the cap and shim off the top of that using what are called shims, which are 4-inch by 4-inch, 1/4-inch thick steel plates. And then they can pull the hand jack out, put another piling in its place, and shim off the top of that, making it a tight fit with the house. So then what I have at all of these locations or these points are these posts or piers where as the house rises and falls, when it gets wet and dry, it can't settle beyond the positions of the piers, okay? That means that we can warranty it for the life of the house. One of the things that I always talk about in terms of warranty that you want to look for as a consumer is that you want to look to see if a warranty has a definition of settlement in it or a standard to measure against in the event of a warranty claim. In order to make that definition of settlement